Hello, this is Ruby. Today we're going to be talking about Chapter 5, Z-scores. So, the first thing we're going to talk about is that any normal distribution can be transformed into the unit normal distribution, also known as the Z-score distribution. If you look at the bottom of the page, just to remind you, a normal distribution has particular properties. Number one is that it is symmetrical. Number two is that the mean, median, and mode are all in the same place, which is right down the middle. The other part of this that we have to keep in mind is that when we're talking about the z-score distribution, that the values for the z-score can range from negative infinity to positive infinity. The z-score transformation always results in having a mu of 0 and a standard deviation of 1 once we've standardized the raw scores. So no matter what your normal distribution had for a mean and a standard deviation, when it's transformed, the new mean will be 0 and the new standard deviation will always be 1. So that's something you always want to remember. The other part of this is that we use z-scores to figure out how far away is our raw score from the mean. So we figure it out in terms of proportions or probabilities. So if you look at the curve, you'll see that between 0 and a positive 1 z-score, we have a proportion of 34.13. Between positive 1 and positive 2, we have a proportion of 13.59%. And beyond 2, we have 2.28%. Now, this would be any score that is above the mean. Because it's above the mean, it would have a positive value associated with it. And that's any score that's to the right of 0. On the other side, because this is perfectly symmetrical, what we have are the scores that are below the mean. So those scores, those z-scores, will be associated with a negative number. Now, what you want to keep in mind is that the proportion or the probability stays the same. So it would be the case that between 0 and negative 1, you would still have that proportion of 34.13%, and you would still have the proportion of 13.59%, and you would still have the proportion of 2.28. So those probability densities are not going to change whether or not you're on the positive or the negative side. Now, why do we use them? Well, for descriptive statistics, we use them for a couple different reasons. Number one is we use them to describe the exact location of a score relative to the mean. So what we're trying to find out in terms of standard deviations, how far away is that raw score that we call x from the mean? Number two, these z-scores are going to allow us to compare scores that have different means and standard deviations using the same metric. So you might have a raw score that's in a distribution that has a particular mean, and then you might have a different raw score that's in a different distribution with a different mean, and converting them both of those scores to a z-score distribution would allow us to compare that. So we're going to go on and show you an example of that. So for most of us, when we compare our grades in French and physics, for many folks it's the case that language is much easier than mathematics. So for many people, French, they would get better grades than in physics. Let's say one day you came home and you entered your dorm room and you found that one of your roommates was very happy. They said, wow, I got a 60s on a physics test. And then the other roommate was sad because they got a 60 on the French test. So you might ask yourself, what's going on? They got exactly the same score, but yet one is very happy and one is very sad. Well, you would probably think about the fact that on the French test, probably a 60 is a low score because most people would probably do pretty well on a French test. Whereas on a physics test, a 60 is probably a high score. So let's investigate that further. All right, so part of how you understand whether or not you have a high or a low score is really determined by others in the distribution. So it's a relative score. So if we look at the physics test, which is on the right-hand side of your screen with the happy yellow face emoticon, what you see is, sure enough, that the mean for the physics test was 50, and having a score of 60 placed you above the mean. So that means you did better than average, so you should be happy. However, with the French test, you had a score of 60 and the mean was 70. So that score of 60 placed you below the mean, so you should be unhappy with that score. Now, how do we figure out those z-scores from a mathematical perspective? Well, we have two computations here and two equations that you can use. So we have one for the population and one for the sample. Please note from the standpoint of arithmetic, they're exactly the same. Essentially in one, you have the population parameters. So you have mu and you have sigma. For the sample, you have m and s, which are the alphanumeric, and those are the statistics. But essentially what you have in order to solve this equation for z is that you take the raw score and you subtract it from the mean and you divide that by the standard deviation. All right, so let's go ahead and complete the first example that we have, which is the physics test. So for the physics test, the first thing that you would do is you would put down the z, which is x minus mu over the standard deviation. Okay, so let's pause and give you a moment to do that. All right, now that you've done that, we will substitute. So essentially, x would become 60. So we'll go ahead and write down 60 for x. Then we have our subtraction symbol. Then for mu, we have 50. So we would go ahead and write down 50, and then we would divide that by 10. So let's give you a pause to figure out what you have as a final z. So what you should have is 10 over 10, which would equal 1. So your final z would be 1. So for our example of the physics test, you would have a z-score of 1, which corresponds to a standard deviation of 1, which means that you are 1 standard deviation above the mean. So this would be a good score. For the French test, we're going to go ahead and use the same equation. So we have z equals x minus mu over the standard deviation, and we're going to give you a couple minutes or a couple seconds to go ahead and write that down. And once you've written down that equation, now we're going to go ahead and substitute. So for x here, we have 60, and for the mean, we have 70. And what you should note right away, that in this case, that our score is below the mean. So right away, you know that that's going to be negative. Now we have 10 over 10, so that's going to give us, 10 over 10 is going to give us a negative 1. So in this case, what we know is for the French test, you're not above the mean as you were for the physics, but instead you're below. And the reason you know you're below is because you end up with a z-score of negative. Whenever you have a negative z-score, you know that you're below. And in this case, you're below negative 1, which means you're below by 1 standard deviation. Okay, so if we compare the two, what we see is that for the French test, we got a negative 1, which means you're below the mean by the distance of 1 standard deviation. And for the physics test, you're above the mean by 1 standard deviation. So this shows us how it is that we can compare two scores that were measured on two different metrics and find out how well you did. So this is our example of showing you how it is that we can compare two scores that were measured on two different metrics by converting them both to z-scores. This also shows you that you can see exactly where you are in terms of your distance from the mean. So for the physics test, we know that you are exactly 1 standard deviation above the mean. And for the French test, we know that you're exactly 1 standard deviation below the mean. All right, so when we look at our normal distribution and we look at our standard normal distribution, which is our z-scores, what you'll see is that the z-scores map on perfectly to your standard deviations. And this allows us to then divide up that standard normal distribution, that z-score, into different percentages, which are simply proportions. So then we're able to associate a particular probability with a particular z-score. And that's going to be what we're going to be doing in the next chapters, which will be chapter 6 and 7. All right, so just to wrap up, I just want you to remember this. I also want to remember it. That when you standardize an entire distribution, what that means is you're going to take two different distributions and make them equivalent and comparable. So that's one thing that's really important about using the z-score. And the other thing that is really important is that the z-score describes the exact location of the score relative to the mean. So I hope this was helpful, and I will have another video to show you some more computations. Bye.